Hello, this is Sean and I'm one of your project leaders from Project B. This video is going to be about a summary of what happened on Monday's seminar. That was seminar 6, where we talked about mass balances. It was a difficult seminar and a lot of students struggled to understand what was going on, so I've decided to make this video to walk through step by step just exactly how the entire exercise was done. Okay, so the first thing you need to know is to do this, to understand what this video is going to be about, I'm going to assume that you have some background knowledge. And the background knowledge that you will need to know is, first, you'll need to know where the general equation comes from. So the general equation that I'm talking about is the accumulation is equal to input minus output plus generation minus consumption. So that general mass balance equation was talked about during project session 3. So if you've forgotten what these terms mean, where the equation comes about, and how it's derived, it's important that you understand the fundamentals before we can move forward. Have a look back in project session 3, have a look through the slides. Otherwise, you can even Google general mass balance equation. So this is mass. And you can have a look where this comes from. The second piece of knowledge that you'll need to know is you'll need to understand terms such as steady state, which we'll be using in this exercise. So steady state, this stuff here was talked about during the seminar 3. We talked about this during the talk about batch and continuous processes and steady state versus non-steady or transient state processes as well. So if you've forgotten where that comes from or what that means, have a look back at seminar 3, which is also on Blackboard. So with this knowledge equipped, we're going to go forward and have a look at the exercises that were done on Monday. The first thing you would have gotten is this page here. And on this page, it would have asked you to find the daily human input of nitrogen into the household's grey water systems. If we have a look at the diagram given, you'll notice that the human input of grey water is only affecting these 3 streams. So these will be the only 3 streams which will contain nitrogen in them from human input. Therefore, what we're interested in is, at this point, how much is the total daily human input of nitrogen, which is this stream right here. That's a combination of these 3. The first thing we do with these problems is we need to draw a system border. So our system boundary is going to cross at this point because we're interested in this point. We're going to encompass all 3 streams because these streams are the ones with nitrogen in them. So it's going to cross here, cross down here, and cross all the way across here. That's our system boundary. Now the reason we do system boundaries is to simplify the problem. By drawing the system boundary, what we're essentially doing is we're drawing a black box over the entire process here. We don't care what's happening inside this box. All we care about are the things that are crossing the system boundary that we just drew. In this case, there are 3 lines that are crossing the boundary. We've got an input over here, another input over here, and an output over here. And they're the 3 lines that we care about now. So with this information, we can add in the information that we know. Up in the question, it tells us we've got 11 milligrams per litre coming in here. So it's given us the concentration. Now we're trying to find this, and we don't know anything about this. So what we're going to have to do is we're going to have to make an assumption in order to do this question. So let's have a look firstly at how much nitrogen is in here. Because we don't know, we can state our assumptions up front. Now normally when you do these questions, you would have to draw the picture yourself and the system boundary. We've saved you a step by drawing you the picture, so you don't need to draw it as the first step. So after drawing a picture, we would write our assumptions. So we would assume, as we know no information about it, that the inlet of spring water, so inlet of spring water, has a nitrogen concentration of 0 milligrams per litre. So there's no nitrogen in that spring water coming in. That's this stream here. because we have no information. And that's a fair assumption because it is pretty clean spring water. There might be some nitrogen in it, but for the purpose of the calculation, we want to simplify it as much as possible. So we're going to say this is 0. There we go. So and we're trying to solve for that. So we've got our 2 knowns and 1 unknown, and we can solve for that algebraically. Now, what we have over here is we have a concentration and we have a flow rate, but we want to know how much nitrogen is in the stream, not just the concentration of nitrogen. So we need to work this out. So what we can do is we can take our 850 litres per day and we can multiply that by our 11 milligrams per litre of nitrogen. This will give us, that crosses that with that, and that will give us a total of 9,350 milligrams per day of nitrogen. That's all we have. So we've worked out over here how much nitrogen is in this stream. We know we can do the same thing over here, but there's no point in doing the calculation because it's going to be 0 times by the flow rate of the stream, which will still essentially give us 0. So there's no nitrogen here, and there's 9,350 nitrogen here. So let's do our mass balance. So the first step in our mass balance is we have to write our equation down. And the general equation that I've shown you before is always the same. Accumulation is equal to input minus output plus generation minus consumption. So we've got that equation. We can simplify that equation by making a few assumptions that we always make early on in chemical engineering. And the 2 assumptions that we would have told you back in project session 3 was we were going to assume that the system is at steady state, and what this implies is that the accumulation in the system is equal to 0. So this cancels out this term to 0. We can also assume that there are no reacting components. So we're assuming that there's no major reactions going on, and nothing is going to be, therefore, nothing is going to be, so generation and consumption are going to also be 0. So that cancels out this term here, and also this term here. All we're left with is this here, and we can rearrange this to give us just input is equal to output, which makes sense logically, of course. What you put in is what you get out of the system. You always need to start with this step to show that you understand the basics. Now, it might seem repetitive and a bit redundant at first, but later on in later years, you'll start having some of these terms not cancelled out. You'll make different assumptions, and it'll be really important to state these assumptions up front to make sure you're using the correct equation. So get into the habit early of doing these steps. So with input equals output, again, we'd go back and we'd have a look at our system. We've got over here input of 0, there's another input here, and there's an output. So our inputs would be, we have the mass flow rate of nitrogen. Remember, we use subscript to designate what we're talking about. So how much nitrogen is in the spring water, plus how much nitrogen is coming in from the humans, is going to give us our output. Our only output is the amount of nitrogen in our outlet. And so you can see that reflected over here. That plus that equals that. So with this information, we can go in and substitute what we know. So we know we've got 0 coming in from the spring water because of our assumptions up ahead, plus the amount in the humans, which we don't know. So this is what we're still trying to solve for. And we've got the outlet, which we've calculated just here. This is the amount of nitrogen in our outlet. There you go. And so this one was 9,350 milligrams per day. We can rearrange for this, and it's a very easy rearrangement in this case, and all this tells us is the amount of human input of nitrogen is going to be 9,350 milligrams per day. And that's all it is. So the purpose of doing these mass balances is, as chemical engineers, we tend to do this so we can solve what the flow rates are and the concentrations are in each stream. and it allows us to make different justifications as why we do things, or where we might need to improve a process or change a certain specification of a process. And we solve for each streams one by one. So we've just solved for what's the amount of nitrogen coming in at this stream here. Okay, so that's the first question. Going across, we go to part 2. And part 2, again, we've made it simple for you by drawing the diagram that we mean here. The important thing to note about this diagram is it's different from the first one, in that this part here is different, coming off. The plants being watered and the toilets are coming from the system itself, not from the spring water. Whereas if you look over here, the plants and the toilets were supplied directly from the spring water coming down. So that's a key difference over here. Okay, so for this question here, we can write in what we do know, which was part of the very first question, as the question asks you up front to label all your streams that you know and the flow rates from what you know. So what we can label up here is, we know this is going to be 9,350 milligrams per day of nitrogen, because we've just worked that out in a previous question. You can go through and label each of these as well. And for each of these, all you have to do is look in the project brief. Remember, the project brief gives you flow rates in per person per day. You've got a 10-person household, therefore you would need to multiply that number by 10. This would give you 550 litres a day, and you'd have 100 here, 200 here, 200 here, check that, and we've got 100 here, 300 here, and finally 100 down here as your flow rates. You also can add up these streams, so these 3 streams combined will give us a total of 850 over here. As it's going straight through, coming in and going straight out, obviously this stream coming through here is also going to be 150 because it doesn't change. Okay, so let's go and have a look at question 2. In question 2, we're asking you, what is the flow rate of spring water into the grey water system? And we've already drawn in the system boundary again for you, just to make things easier. So that's that system boundary 1, which is the big one. And we're asking you, how much spring water is coming in at this point here? That's what we're trying to find. By drawing this boundary, again, we're blacking out the entire section in the middle of it. We don't care what's happening inside. We only care about what's going on at the points where it crosses that system boundary. So we've got here, here, and down here. So there are a few things that we can work out here. The first thing, we're looking at how much water is coming in. We have no idea about the water coming in here because we're not told anything. So again, we need to make an assumption. So the first thing we do for this question is, new page. Okay, so I would assume there is no water in the human waste. What does that imply if I wrote it out? Well, that implies that the mass flow rate of H2O, which is water, is going to be 0 for the human stream. That's the human stream. Okay, so I can do a mass balance now across this entire system. So what I want to know is this. Now down here, I can work out what this stream is down here. And that's quite simple because I can see there's 100 and 300 to make up this stream. So this stream would be a total of 400 litres per day. I'm going to not write the units to try and keep this nice and simple. Of course, in your actual report, you make sure you write the units on there. Okay, so doing a mass balance, I would, again, write out the entire equation. So that was the accumulation is equal to input minus output plus generation minus consumption. Then I'd have to assume it's at steady state, like I did before. Now I'm just going to write this shorthand just so it's faster. Steady state, and we're assuming no reactions. So same as before, but you would normally write it out fully. This would cancel out these terms here, here, and here to 0, giving us just input is equal to output. Okay, so from this point, again, let's look at our input streams. Our input streams are going to be spring water coming in. We've also got human waste coming in, and then our output's this stream here coming out here. So we've got in, and we're just looking at water this time. So I'm going to go the mass flow rate of, what are we looking for? Mass flow rate of water, so H2O, in the spring, plus the mass flow rate of water in the human waste stream is equal to the mass flow rate of water in the garden irrigation stream, which is the bottom stream. Okay, substituting in the numbers that we know. We don't know this, so this is the same thing, because this is what we're trying to find. We've assumed this is 0. Over here, garden irrigation, we've just worked out that was 400 litres a day. And of course, easy equation to solve here. That tells us the flow of spring water is just going to be 400 litres a day. And that's what we've just worked out. So that's how you would set it out, and this is how then you've just worked out what the stream is. So we now know this is going to be 400 litres per day coming in right there. That's question 2, and that's what we wanted you to do for all of question 2 here. So for question 3, assuming that the grey water treatment does not reduce nitrogen concentration, what is the nitrogen concentration in the grey water recycle loop? Going back to our picture, there's a few points. There's one important point that I need to make here. A lot of students pointed out that if we're just adding nitrogen and the grey water treatment system is not removing anything, like the question said, won't there be a buildup of nitrogen here? And the answer is no, because there's still nitrogen being removed in the system. And the nitrogen is being removed out of this stream here. You'll notice as it goes through, you're putting in nitrogen in here, it comes through to the system. The question tells you the system doesn't treat anything, so the nitrogen passes straight through, comes around to this point, but then the stream is split off in 2 directions. So some of the nitrogen in this stream is actually diverted into the garden and the toilet, and some of it's recycled back. So you do have some removal of nitrogen still going on in your system. We're just saying that there's no nitrogen being removed by the grey water treatment system in that question, which is what is meant by here. The grey water treatment system does not reduce nitrogen concentration. Okay, so for this question, we're looking at doing a balance over nitrogen this time, not water. The previous one we did a balance over water, so mass of water. Now we're looking at the mass flow rate of nitrogen. Again, we're going to use the same system boundary because we're trying to find what the flow rate, what the concentration is in this stream here, which is what the question asks. This recycle stream, what is it? Because at this point the stream splits into 2, this doesn't change the concentration at all. All it does is it changes the flow rate. You're essentially halving, or taking 40% of the stream off this way and putting the rest through that way. So if we find the concentration of the stream here, it's going to be the same as the concentration of the stream here, which is the grey water recycle loop, and that's what we're trying to solve. Therefore, we can just use the same system boundary as the first question, number 1, because it takes into account the stream that we're trying to find right here. So using that, again, we have 2 inputs. We've got input here, input there, and an output here. But this time, we're going to do nitrogen. Now, remember earlier on, we've already assumed that the nitrogen in the spring water is 0 back in the first question. So we have a nitrogen concentration of 0 over here. And we know there's no nitrogen in here. We know our nitrogen is coming in all through here. So if we do another mass balance again, and we write it out fully, remember you would take these same steps early on and cancel out until you get to this point. I'm going to skip those first few steps so I don't have to rewrite them again. Again, you'd be input is equal to output. So this is question I over here, and this is question I. Input equals output. Now this time our inputs are the same, so we're going to look at the mass flow rate of nitrogen, so how much nitrogen is in that spring water stream. Our other in stream is going to be the human, is equal to how much is in the garden and irrigation stream. So similar to that before, because we haven't changed our system boundary, it's going to be exactly the same. Now let's substitute in what we know. we assumed there was no nitrogen in the spring water earlier on. The amount of nitrogen that's coming in from the human waste was 9350, which we found earlier in question I. And now we're trying to solve for how much is in here, because we don't know this one in irrigation. And once again, it's a very simple mass balance that we're asking you to do. All you have to do is solve that question, and that just tells you the mass flow rate of nitrogen in the garden irrigation stream is just going to be 9350 milligrams per day. Now this is a flow rate, milligrams per day. The question, if you read, is asking you for the concentration of nitrogen. So we want to solve for that. The concentration would be given to us in milligrams per litre, or something like that. So we need to get to a unit of this. What we do know is we know how much the flow rate is in there. So we can actually work out what is the exact concentration by taking this number and multiplying it by the 400, which is 400 litres per day. There we go. So we can use these two numbers to work it out. If I have a look at this, I can just go 9350. I've got milligrams per day. Now I want these units to cancel out, so I'm going to have to divide by my 400 litres per day. Because I'm dividing, these units will cancel out with these units and put the litres on the bottom. This would give me a total of 23.4 milligrams per litre by doing that. So I've worked out what my nitrogen concentration is, and this is nitrogen concentration. Seem to have a bit of a problem focusing, so I'm going to try and focus that a bit. There we go. Okay. So it's important to keep in mind, is it asking you for a mass flow rate per day, or is it asking you for a concentration as the answer? In this case, we wanted the concentration, because the concentration is what is governed by WHO guidelines and other drinking water guidelines. So the concentration is what we want. So what we just found here is, here's our 400 litres per day, and we know in here there is going to be 23.4 milligrams per litre. So as you can see, we're slowly solving each stream one by one and working out what is in each stream. Alright, so let's keep going. In question 4 now. Each question links on from the previous question, by the way. So in question 4, what is the concentration of the water delivered for the household use for bathing, dishwashing and laundry? Bathing, dishwashing and laundry. Does this meet appropriate guidelines? And again, we've told you, let's just use this in boundary 2 to save you the hassle of trying to figure out where the boundary is. Having a look at this, we're interested, the question was asking us, what is the concentration of nitrogen coming in at this point here? Because this point here is what is going into the household. Remember, that's bathing, dishwashing and laundry, right here. So to do that, we can draw a boundary that crosses this line because we're interested in calculating it. And that's this number 2 one. We're using this one because we have information about this stream already, which we worked out before. We also have information about this stream because we've worked it out down here. Remember, these two streams have similar concentrations because they're splitting off from the same parent stream here. Okay. So let's do a mass balance over this area, and we're looking at nitrogen, so it's going to be another nitrogen mass balance. So coming down here, again, I'm going to skip the first few steps and go straight to input equals output. We're going to look at the different streams that we have. Input streams. We've got 2 input streams here and here. We've got 1 output stream over here. Okay? So our inputs are going to be mass flow rate of nitrogen in the spring water plus mass of nitrogen in the recycle is equal to the mass of nitrogen going into household. Remember, you can call these whatever you want, but it's important to label what they are on the diagram if you're writing a report, so the reader knows exactly what you're talking about. Alright, let's go back to here. Let's have a look. Mass of nitrogen in the spring water, we know this is 0 already. We're looking at how much nitrogen is going to be in the recycle loop, and we know information about that again. So we know it's going to be 400 litres a day, and we've got 23.4 milligrams per litre, but we want it in a mass flow rate, and a mass flow rate is given to us in milligrams per day. That's what we want. So we want this sort of number over here. So we can do that. Again, we can work out what the milligrams per day is by doing some basic maths. So we have our, before we do that, sorry, we need to work out what the flow rate is for this stream. We know it's 400 out here. We know it's 850 coming through here. So if 850 is being split off into 400, all we have left here is 450 litres left, litres per day. So that plus that will give us the 850 of the original stream. Now, concentration in this stream is the same. Concentration in this stream is still 23.4 milligrams per litre, because they're the same concentration, they're coming from the same stream for this stream and this stream. So the same. And over here, we also know that this is going to be 23.4 milligrams per litre. The concentration doesn't change when you split the stream. Okay, so with that information known, we can calculate the mass flow rate of nitrogen in here by multiplying those two numbers. So over here, we can take 23, so plus 23.4, and this was in milligrams per litre. And I'm going to multiply that by my 450 litres per day. That gives me, and the mass nitrogen into the household is what we're trying to find. So we don't know this one yet. That's what we're trying to find. And again, we can do some simple maths and calculate and work out what this is. This is what we're trying to find. And what we find is the mass flow rate of nitrogen into the house is just going to be 12.4 milligrams per litre. So now we have this mass flow. Rate of. Oh, sorry. One more thing. We would get. Don't have a calculator. Let me pull up a calculator quickly. It's not that number. Pull the number out of nowhere. So it's 23.4, and I'm going to multiply that by 450. This will give me 10,530 milligrams per day. Now again, the question is asking for us for concentration. If we have a look at the question sheet, we want nitrogen concentration, and again, concentration is given to us in milligrams per litre. So we're going to have to do something about this number over here to get it into our milligrams per litre. We know about the flow rate in this stream here, because we can see that it's going to be all these streams combined give us this flow rate, and the total of these streams is 850. So in here we have 850 litres of water. So we can take that one, and we can take our 10530 milligrams per day and multiply this one by, we'll need to divide by our 850 litres per day, which will cancel out the units here and here and put the litres on the bottom. This will give us a final number of 12.4 milligrams per litre. This is our concentration of nitrogen into house. So that's what we've just found here. So originally we found this number here. This was the mass flow rate of nitrogen in, and we've converted it to a concentration in this stream by dividing it by what the total flow rate of mass going through, which is 850 litres per day. So that gives us 12.4. Now you got your 12.4, and what it asks you in the question is, does this meet the appropriate guidelines. And from your project brief and from your research, you'll know that the appropriate guidelines are, the guidelines are 11 milligrams per litre as the safe limit. So you can see that this number here is going to be greater than your 11 milligrams per litre, and it would not be safe for the household to use because it's too high. And that was the purpose of doing the mass balance. We found out if the grey water treatment system does not treat any of the grey water and does not remove any of the nitrogen, then there's going to be too much nitrogen in the household for us to use. So we do need to remove some nitrogen for the system to work. So the question becomes, okay, what's the next step? We need to figure out how much nitrogen we need to remove from our system. So carrying on, we're going to go to question 5. In question 5, we see that, okay, we want to reduce the nitrogen to a safe concentration of 10 because 10 is less than the 11 written in the guidelines. So assuming that we wanted to treat it to 10, what do we need to make sure the nitrogen concentration in the recycle loop is so that we get a 10? If I put it in the picture, now I'm going to maybe use a different picture just because that one's quite cramped at the moment. Say we have a look at this picture here. So what it's saying is, if we want 10 milligrams per litre in here, which is the safe limit, what do we need this stream to be over here? Coming in here, what concentration in here will make it so it's 10? Because with the current concentration, this is 12.4 and it was too high. So we're trying to solve for this. Because we're trying to do that, again, we can just use the system boundary number 2 right there. And we know everything about this stream. We know stuff about this stream as well. So we can calculate for this bit right here. So going to the calculation, I'm going to go to my input is equal to output. The streams I have going in, I've got my spring water, I've got my recycle, and that's going to give me mass flow rate into the house. So this time what I know is I know things about my household. I want to know something about this is what I don't know, and I already know everything about this. So this is again going to be 0 because we know this. We're trying to figure out what we need in the recycle this time. And in our house, what do we have? Well, in our house, we know we need 10 milligrams per litre. Now, we're asking for a mass flow rate, so we're going to have to multiply this by our flow, which is 850 litres per day. So if you forgot where the 850 comes from, the 850 is when we added up all these streams coming from here to 850. This will cancel out with this and give us a recycle mass flow rate of 8,500 milligrams per day. Now again in the question, it's asking us for nitrogen concentration once more. So we need to work out what the concentration is. If we have a look at this, we'll do the same thing. We have 8,500 milligrams per day, and we will divide this by our flow rate, which was 450 litres per day. And the 450 was from here, which we worked out earlier. By calculating from this minus this will give us that. So we do this, and our units again will cancel out, bringing the litres down. And this will give us a total concentration of, let me check that one, that'll give me 18.9 milligrams per litre. And this one that is the concentration of nitrogen in our recycle. So that's what we need if we want to hit the safe limit within the household. So we've just figured out we need 18.9 in here, but we currently don't have 18.9 in here. We currently have 23.4, which we worked out a lot earlier. So that's the limit that we need. So the question now is, if we need this much, how much Nitrogen then needs to be removed from this point to ensure that this grey water recycle loop has the required 18.9, because it currently doesn't, it has too much. So to do this, we need to have a look at our next mass balance. That's the final question, which is part 6 over here. I'm having some focus issues again, so I'm just going to adjust that. That should be a little bit better. Okay, and the last question, what is the required reduction in the grey water system? Use boundary 3. So how much are we removing out of the grey water treatment system? So for this part of the question, we know that we need 18.9 to come out of here. We need to know how much grey water, or how much nitrogen is in here, so we can calculate how much to remove out of the system. If we have 18.9 here, what is this? So that way we can know how much to remove out here. To calculate what the nitrogen concentration is in here, we can do a mass balance with order 3, because we care about the stream which crosses. We already know stuff about the human input stream, and we know everything about this stream over here, which is what we just worked out earlier. So we have enough information to try and solve for what's in this stream over here. Again, we're doing nitrogen, so it's going to be a nitrogen balance. Let's start a new section. Do all your initial assumptions, cancelling out, and you'll get back to input is equal to output. The in streams that we have, the human stream, this stream going into the household, the stream coming out of the household. So input streams, we have nitrogen coming into house plus nitrogen of humans equal to mass flow rate of nitrogen coming out of the house. That's what I call them. Mass of nitrogen coming into the house, we worked that out before. That was this stream here. And that stream we know has a total of, where are we? Nitrogen should be, let me find that one again. Mass flow of nitrogen is, yeah, there it is. 8,500 milligrams per day, plus how much nitrogen is coming in from the humans. We worked that out from very early on, which was 9,350 milligrams per day is equal to the mass of nitrogen coming out here. So this one was, we don't know this, so we're trying to work this one out. There we go. So we don't know that one. We can add these two together to figure out how much mass nitrogen there is, and that will give us a total figure of, what have we got here? 8,500 plus 9,350, 17,850 is equal to how much mass flow of nitrogen we have coming out of the house, and that's in milligrams per day. So again, we don't want milligrams per day because we're interested in the concentration. So we'll do once more. We'll divide this by this number here, which is the 850, because that's our flow rate. So if we divide this by 850, we take the 17,850 milligrams per day, and we'll divide it by 850. That's liters per day. This will give us 21 milligrams per liter. And so here we have the concentration of nitrogen exiting the house. So that's there. We've just worked out that this one is equal to 21 milligrams per liter. Over here we have a nitrogen concentration of 18 milligrams per litre. Okay, so in the question, it asks us how much nitrogen needs to be removed. Well, we can see that we have 21 here, we have 18.9 here. Now again, you could do it if you wanted to show it all working out properly. You could draw another system boundary around the grey water treatment system and work out how much is coming out of this stream, because you've got input, output, and output. You can do the same thing with the mass balance and work it out. Or, since it's a pretty simple question, you can just have a look at this and go 21 minus 18.9. So I'll take my 21, which is my before, I'll subtract my 18.9, which will give me 2.1 milligrams per litre is how much I need to remove out of my system. So this stream here, I need to remove 2.1 milligrams per litre of nitrogen to ensure that my household system is operating within WHO guidelines. And that's the entire working out. So in this last part here, again, I could have done the input minus output and written the entire process out. What I've just shown it to you 6 times, so I'm not going to do it again. That's what it becomes, and that's what you get. So when you get to that point, then you'd have a think about my technologies that I looked at in my literature search. Does my technology remove 2.1 milligrams per litre? What sort of removal efficiency or removal rates can I achieve with my technology? And this is why we do mass balances, because we can see whether the technology chosen is going to suit our system or not and give us the correct numbers. So that's it for mass balances. I hope that cleared some things up. There was quite a lot to go through, and well done for getting through the entire video. Until next time, this is Sean. Good luck with your projects.